Okay, so I need to talk about a few random linear algebra things, just so we can continue on. So the first thing is the commutator. So a commutator of two operators, O1 and O2, is just going to be O1 times O2 minus O2 times O1. So this is also an operator. And we can work this out. For a specific example, we can take our SX and SC operators and calculate the commutator. And you could do this using the outer product expansions, but I'm just going to do it using our matrix representations. And so if you do that, I have Sx times Sc minus Sc times Sx. And if you work out all the matrix math, you'll find that this is equal to minus I times Sy. And all we care about for now is that these operators don't commute. And whenever you have two operators that don't commute, it means you can't label your states, your basis states, using both of these values. So we saw before that we wrote our general state vector for a spin 1/2 particle as either linear combinations of our Sx cats or as linear combinations of our Sc cats, but not as, we didn't label them by both values. And that's related to the fact that these operators don't commute. So, and obviously, if they commute, then that means it doesn't matter what order you apply the operators. So acting O1 and then O2 would be the same as acting O2 and then O1. So another thing we can do is have functions of operators. And those are going to be defined in terms of the Taylor expansion of the function. So for example, if I had e to the O, where O is an operator, I would work out what that is by using the Taylor expansion of just the function e to the x. So the Taylor expansion of e to the x is just 1 plus x plus 1/2 x squared plus so on, infinite number of terms. So that means this operator, e to the O, is going to be the identity operator, which is like 1, plus O plus 1/2 O squared plus, again, an infinite number of terms. And although there are an infinite number of terms, and that's not an issue, as we'll see. So one interesting property that functions of operators have is if I, so let's see what happens when I apply e to the O to an eigenstate of my O operator. So how I can work that out is I can just write out this Taylor expansion for this operator. And so each of these terms will act on O. But we know how O acts on our O eigenstates. It's the same as just multiplying by the eigenvalue, O. And maybe I should have used a different letter, but whatever. We're sticking with it. So I have this. So this is just 1 plus O plus 1/2 O squared plus blah, 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 an infinite number of terms. And we can just read that off. Well, this is just the Taylor expansion of e to the O. So what that tells us is that when we have a function of some operator acting on an eigenstate of that operator, the function of that operator, the eigenstate will also be an eigenstate of this function of the operator with eigenvalue f of, in this case, O. And so we've seen that here. E to the O acting on the O eigenstate just gives you e to the O times O. So it's easy to work out functions of operators acting on eigenstates of the original operator. And it'll be very useful in the upcoming videos. And then just a little thing, the commutator of a function of an operator with the operator itself is 0. And again, you can prove that just by writing in this Taylor expansion. And so you'll just have a bunch of terms, but an operator commutes with itself. So it would commute with all these terms, and hence it commutes with this function. So the last thing to talk about are called the angular momentum raising and lowering operators. S plus is the raising operator, and S minus is the lowering operator. And So for the spin 1/2 system, we're not going to talk about them too much. It's kind of a trivial case, but for other systems with higher angular momentum, they will be very important. And so basically what they will do is they will take you from a state of angular momentum, like pointed along the z direction, and they will take you to a new state where the z component of the angular momentum is higher or lower. So, for example, in our spin 1/2 system, we just have spin up or spin down. So the z component can be either plus h bar over 2 or minus h bar over 2. So, and these are just the outer product representations, which you can work out if you and they're defined in terms of the sx and sy operators like this. So if you work it out in the SC basis, you'll just find this outer product representation. But what we find is if we act s plus on the minus ket, we get something that is proportional to the plus ket. So we've kind of increased the z component of the angular momentum on our state. And we also get an h bar, but that's whatever. And then similarly, if I act s minus on the plus state, I will get an h bar times minus. So the lowering operator has got me to a state of lower, the z component of the angular momentum is less, whereas the plus ket gets me to a state where the z component is more. And obviously, since there's only two states, it's kind of simple how it works out. But when you act s plus on the plus state, so for a spin 1/2 particle, the maximum z component you can have is 1/2. So if you act s plus on the plus state, well, you can't go any higher. So you just end up with 0. And then similarly, if you act s minus on the minus state, you can't go any lower. So you also get 0. And we'll be able to define these operators for more higher spin systems, and then, it'll become more useful there.